plugging it in makes a big difference. So we're going to pick up from where we left off last time. And what we discussed last time was the general idea of a tree that has lots and lots of children. And we discussed some pros and cons of this, some reasons to do this, what have you. The primary kind of initial motivating reason to go to a tree with many children that we discussed had to do with the memory hierarchy. That is, we have a trade-off between search and insert in a node versus the number of cache misses in the CPU. And so this basic form of multi-child tree is known as a B tree. And we looked at a specific instance of it, the 2-3 tree, which you can think of as a B tree with a really tight limit on the number of nodes. But a B tree can expand well beyond that. And then we're not going to be implementing that, but I introduced it for a couple of reasons. First, to give you a sense as to what tends to be used in practice for a search tree. And secondly, by introducing the idea of multiple children, it gave us a chance to talk about something we will be implementing, which is the trie. And so we introduced it briefly, but today we're going to go over it in considerably more detail. So here we go. When we think about building a trie, we have a root node that contains some number of children. But what children it contains depends heavily on what values are being explicitly represented within the context of the trie. So the approach we're going to discuss today and the approach we'll be undertaking in our lab this week is that at each node, it's going to have within it a sorted array of pairs, where in each pair we have a character, and then we have a link to a child node. So the concept is that for every character that's present in the trie at that present level, we're going to have an outward going link to a child node. Okay? So what's that typically going to look like? Let's go ahead and build a trie and add some words to it so we can get a feel for how this kind of thing might be put together. So the first word that we will add is at. So when I mentioned that a node contains a sorted array of pairs, where each one is a character with a link to a node, the way I'm going to represent this when I'm drawing it is going to be to annotate the edge coming down to the child with the letter that leads outward from that node to that child. So unlike the binary search trees and the B trees and the 2-3 trees and so forth that we've discussed already, in the case of a trie, you can actually think of the data as such as being stored in the edge rather than in the node. That's just a conceptual aid. Of course, ultimately, everything's inside of a node. But the point is, within the node, we have these associations between this character and this outward pointer, this outgoing pointer. All right, so I'm going to add at to my trie. So I'm going to have a child node, and that one is going to be annotated by the letter A. And then I'm going to have another child node, and actually I'm going to move it around a little bit because I know what's coming. That'll be annotated by the letter T. And then we have this terminating node down here. Now, the nodes themselves do contain one fairly crucial piece of data in addition to the outgoing links. And that crucial piece of data is whether or not that node represents the completion of a term that's a member of the trie. And so that can just be represented using a Boolean. So you've got a Boolean, and for now and for this lab, we're going to be using these tries to represent sets of words. And so this Boolean value, I'm just going to call is member. So in other words, is this a member of the set of words that I'm trying to represent? And so if that's true, then yes, it is a member of that set. If it's false, no, it's not a member of the set. We'll talk about the difference that makes in just a moment. So when we get down to this node T, we would say, yeah, it's true. That's a member of the set. At this node A, on the other hand, that would be false. The word A is not a member of the set unless we explicitly add it to the set at some point. And so the reason for this distinction is that every prefix in the trie has a corresponding node, but not every prefix actually corresponds to a word that's a member of our set. And so at each node, we need to annotate that. But it's entirely possible to have words that are interior nodes, but are still members of the set. Like A is a legitimate word. And so if I were to add it to the set, this false would become a true, and it would be one of the words that we actually have in place. Any questions about that so far? Okay, so the next word we're going to add will be ant. So when we come in to add ant, we come to the root, and we see, yeah, there's a child for the letter A. So we follow that down, but there's no child for the letter N. So we're going to create one. Whoops, N goes here. And now it needs a child for the letter T. And then here, these are not members, these are members. So we have at and ant so far. So now we'll add just a couple more words and get a feel for what this looks like. Let's see. We're going to add bar. So we come to the top, the root node. B is not yet a child, so we're going to have to do an insert into that array, and we'll insert the letter B. And there's a node coming off of that, and B is not a member of the set. Then we're going to insert an A. Whoops. Let me try that again. We're going to insert an A. And Ba is not a member of the set. And then finally, we are going to insert the letter R. And that is a member of the set, and we're done. Can I help you with something?
I don't have. I forgot to grab a pencil on the way out.
Okay. Do you need a pencil?
Yeah, because for.
Okay. Then go get one.
Am I going?
Well, if nobody has a pencil, you have a pencil you can spare? All right. Professor Simi will enable you to write. Okay. All right. So we've added the word bar to the set. Now we're going to add the word barn. So when we add the word barn, we come into the root. There's already a node for B. There's already a node for A. There's already a node for R. So now we're going to add a node for N. And so notice here we have a leaf node that corresponds to a member of the set. Here we have an interior node that corresponds to a member of the set. but these two nodes are interior and do not correspond to members of the set. Yeah. Any questions so far? Any questions? So that's insertion into a trie. Let's think about searching it. So when we search a trie, there are a couple of different kinds of question that we can ask. We can ask if a word is a member of the corresponding set. So I could ask this trie, is the word "an" a member? So I come in and I see, yeah, there's a letter A, so I'll follow that. There's a letter N, I'll follow that. But it ends in a node with a false value, so I'm going to return false. It's not a member of the trie. Now in contrast, let's say I have the word "ant." So I can come in and I see A is there, N is there, T is there. And at this point, I find a node with the value true, so I return true. It is a member. But now we're going to do a slightly different kind of search. In this different kind of search, this is going to be a prefix search. So in this prefix search, I'm going to ask, what words are there that begin with the letter A? So I come in, and at the letter A, I stop here, and then I ask the question, are there any children? And if there are, now I actually want to return a whole list of words. Every word that's rooted at this subtree. This indicates the fact that we need to have some notion of traversal in order to enumerate these strings. The tree, being an intrinsically recursive data structure, lends itself to the idea that if we can define what traversal means in terms of the root node, that exact same definition will also apply in the context of a subtree. We just have to stick our prefix in front of everything we find in the traversal. So we're going to think about the overall process of conducting a traversal of the trie, and then we're going to see how it applies to the idea of a subtree and see where that takes us. Any questions on any of this so far? Okay, so let's think about the idea of traversal. A key part of the idea of traversal is the fact that at each node, we are maintaining this array as a sorted array. So when we do our traversal, we want to keep everything in this sorted order. The sorted order is both something that enables the searching of the tree to be a little more rapid. It also enables us to produce this canonical order of words. If we think about the application domain of typing in a prefix on your phone and wanting to see all possible completions of that prefix, we want to see them in alphabetical order because it's what we're used to looking at as humans. If it came in some crazy permuted order, we would likely find it somewhat disorienting. I think it's safe to say. So, traversal then. Traversal is a matter of starting at a given node and recursively first checking to see at the current node, is it a member of the trie? And if it is, you add it to the strings that you're returning. And, okay, Morgan, put your phone away immediately and do not take it out again during class.
Sorry.
Yeah. If you need to, turn off the ringer, turn off the vibrate, whatever you need to do to avoid distraction. So, coming back here, if it's a member, we add it to the list of values that we've located in the trie. If it's not a member, we just continue recursively with the children. So let's explore this trie and see what kind of traversal we are able to produce. So we start at the root node, and the first question we ask ourselves is this a member of the set? And in retrospect, I really should have put something there about it. What would it mean to say that the root node is a member of the set of strings described by the trie, if that were to be true?
That's false.
Well, I will assure you there's a reasonable interpretation of that node having a value true.
Is a blank space?
It's blank, not even a space. A space is a character after all.
Yeah.
But but you had a good insight there, Morgan. If this node has the value true, it means that the word of length 0 is a member of the set. And a word of length 0 is a legitimate value of the string type. It's something well worth considering as a possibility. Now, in this case, of course, it's not. And so we get to the root node and we see it's not a member. So we will just go in sorted order and call this recursively. So we make a recursive call on the A node. So we go to the A node and it's false. So we don't need to add anything to our list. So we make a recursive call to the N node. So the N node is false. Again, we don't add anything. So we make a recursive call to the T node. We get to the T node and it's true. So we actually have something that we can add to our list. Whoops. Let's come back there. So we're going to start creating our list over here. And so when we create our list now contains the word T. That's kind of unsatisfactory. So there are actually a couple of ways we can conceptualize this. One approach we could take would be you get to a node, you find it's a member, and then you just return an empty string. Then, as you return from the recursive call, at the node above, as it processes its return value, it prefixes whatever character was associated with the edge from which it's now returning. So you can imagine this coming in as an empty string, and then here it says, okay, that needs a T on it. And then coming up here, it says, oh, that needs an N on it. And then coming up here, it says, oh, that needs an A on it. Actually, we're not even there yet. Let's just say we've got an NT for now. And so the reason we're not there yet is we have to now check out the other child before we return from the recursive call. So we go down here and we find out that T is true. And so we're also returning, a T in our list of words. This recursion now completes, and now we stick A's in front of both of them. And so notice that thanks to the left to right ordering that we're doing, they're both coming back in alphabetical order. So now we come back up here and we descend the next child, which starts with the letter B. So that's false, that's false, that's true. So we have an R. And then even though we've added R to our list, there's a child. And so we actually keep going. And we come down here and there's a true. So we have an N. And then as that N returns, it gets an R in front of it. And then as both of these return, they get A's in front of them and B's in front of them. So that's one approach that we can take to taking this sort of compact encoding of our words in the trie and then rebuilding them as we traverse them. Another way you can think about it is to have the trie send the prefix down as it goes as part of what the recursion is doing. So we're going to walk through this again, taking that approach. By the way, this traversal that I'm doing, what is it most similar to? Is it most similar to a pre-order, an in-order, or a post-order traversal that we saw in the binary search tree? Post-order? How so?
You already have it sorted, and then you start from the bottom.
So I see what you're getting at there, especially with the way that I've been building these. This approach is actually kind of a mix of pre-order and post-order. On the pre side, it's adding words to our list. On the post side, it's sticking letters on the end of them. So actually, it does have a strongly post-order feel to it. Yeah, I like it. It's a good way of thinking about it. Setting the prefix first then is more of a pre-order way of thinking about the traversal. So that's what we'll look at now. So if we think of this in a pre-order way, then from my initial call, I send down the letter A to whatever I happen to discover down here. So this is false, so there's nothing to add. False, nothing to add. False, nothing to add. But now I'm going to send an N down to whatever I discover. And now I come down here and I'm going to send a T down to whatever I discover. And then it's true. And so I've got an ant. Coming back up here, I'm sending an A down. And then I send a T down. And bam, I'm done. I come back up. I send a B down. I send an A down. I send an R down. And of course, this is a true one, so that actually has to be included in my list. I'm sending a BAR down. And then I send an N down, and I get true. And so that's a pre-order way of thinking about this process, as opposed to the post-order way of thinking about it we discussed earlier. Well, in order really isn't your friend here, because reconstructing the word requires doing either pre or post processing. There just isn't a whole lot going on inside the node. And so in order winds up being not as helpful a traversal strategy in this particular case. But pre-order and post-order each have their benefits. They're really just equivalent to each other, of course. You could do it either way. So if we think back to the motivating example I mentioned earlier, which is what is everything starting with the letter A? I search the trie and I find there's an A path over here. And now I do my traversal of this, and I either send my A down or I append my A to whatever I receive back, whichever you prefer. And so when I do that, of course, I get both ant and at. And that's how I can use this to do text prediction outright, is the subtree contains every possible thing that could follow from that letter, which is pretty cool. Any questions so far? Okay, let's think about deleting from a trie. So there's both a simple answer and a complex answer to this question. Just looking at this, if I wanted to delete bar from the trie, how would the data structure need to change? That's exactly right, Caleb. You would change the R from a T to an F. Okay, that F gets an F. Bar is now no longer a member of the trie. That's the only change I need to make, and it's actually the only change I'm able to make. And the reason I say that is this node needs to stay in the tree. Because if this node goes away, then its children are affected accordingly. Now, let's think about a different kind of scenario. Imagine you've got bar and barn. And let's imagine I delete barn. It is sufficient to change this T to an F. If this is all I do, I have a correct solution, because when I do a search, when I search for barn, it'll get here, but it's a false, and so it's not going to return true that it's a member. If I do a traversal, this is a false, and it's not going to include it in the enumerated list of things that were traversed. So this is a correct solution.
So in rare cases, it'd just be smart to get rid of its what's it called, value, or change it to false.
You can always change it to false. That's a sufficient solution. Now, if that's all I ever do for removal, is this in any way unsatisfactory?
No.
Is there anything looking at this that seems, yeah, Elijah?
You use memory.
I'm using memory that I don't need to use, right? I am occupying strictly more RAM than necessary to represent my data. Now, how big a problem is this? Well, as always, it depends, right? It depends on the overall footprint of the system and so on and so forth. Let's say I am making frequent additions and removals, okay? If I'm making frequent additions and removals, I probably don't want sort of garbagey nodes hanging around. So at that point, you could imagine remove as a two-stage process. First, you mark as false whatever pertinent node there is. And secondly, maintaining a reference to the thing that you marked as false, you check to see if it has any children. And if a node is false and has no children, it can be removed. Now let's imagine bar had also been removed. Having removed that node, this node is now false and has no children.
And then it repeats for the entire cycle.
That's a good guess, right? So removal in this sense proceeds upwards recursively through the tree.
It's like burning off. It's like cutting down a branch. It's like cutting off a branch bit by bit.
Yeah, kind of. And so that's removal right there, is just at each, starting at the node you marked false, does it have children? And if it does not have children, it goes away. And much as the removals that we did in the binary search tree, the easiest way to implement this is probably just to return a node to whatever should be present and returning an optional empty if there shouldn't be anything, and kind of going upward from there. And so that enables efficient removal from a trie. So we've looked at inserting, we've looked at removing, and we've looked at searching. Any questions so far?
Nope.
So this is a pretty straightforward data structure, but it's a really powerful one. So we're going to spend some time now thinking about how we analyze the performance of this data structure given certain kinds of workloads. And there are a couple of different values that we need to keep in mind as we analyze the performance of a trie. Time is what we're analyzing, yes. So looking at how we've employed this, what are some pertinent factors in the input that we would have to think about when considering the time? You can state them informally. What affects its performance? Absolutely, n, the total number of nodes. That's huge. Right? That's going to be very important, although in some subtle ways. What are some other factors?
The length of each branch, I guess.
So the length of each branch. If we consider length as depth, in other words, how deep does it go, then yeah, we've got something relevant there. So we'll call D the maximum depth. What are some other factors that might impact the performance of a try?
Well, no, we've already done that because that's the total number of nodes.
But how many different like branches from a single value? So A, then A in or A B, all that.
Good. We're going to call that B, which is the branching factor. Let me rewrite that. B is the branching factor. So in other words, what's the maximum number of children that any node has in the tree? Note that both for D and B, we're talking about the maximum present in the tree. That turns out to be a really useful way to think about what the try is doing. Because we are, after all, with the big O notation, trying to devise an upper bound for performance. So in devising an upper bound for performance, what we do is we imagine, given that we know the maximum depth, then any leaf is reachable in D steps or less. Given that B is the maximum branching factor, we know that any node is reachable in B steps or less, or rather, any node is resolvable in B steps or less. So let's try to put together some expressions for the time complexity of the try in terms of these values. So why don't we begin with thinking about an add. So adding a value to the try. How many operations is it going to take in terms of N, D, and B to add a value to the try?
A couple. Let's see. You need to check for placement.
It needs to check for placement. Good. How expensive is it to check for placement within the node? We won't even just say check for placement. We'll talk about actually placing, right? Because we may have to add a value to the array that we have in our node. So how expensive is it just to update the node for a single letter? What's that?
It's not very expensive.
Okay, but using these values, how expensive, how can we express how expensive it is? How many operations is it in terms of one or more of these values? How are you going to combine it? Are you going to add them, multiply them?
I could say it's multiplied. So I say D times B times N plus 1.
Okay, we have a suggestion that it's D times B times N plus 1.
Well, the N and plus 1 are in parentheses.
Okay, how did you derive that?
Because the number of nodes is, N is just the number of nodes in the tree that it needs to check against. It needs to check.
Does it need, when inserting, to check against every node in the tree?
No, but it needs to check, well, it needs to check for the correct node.
Yes, and in order to do that, does it need to check every node?
No,
So why is this here?
I don't know. I just didn't.
Okay, so let's back up and think about it again. We've got these three values. We're inserting one word into the tree. We're going to assume the word has a length which is equal to D, the maximum depth. How many operations do we need to perform to insert the word? Yeah, Graham.
It'd be D times B.
Whoops. D times B. How did you get that, Graham?
Because it's at max, it's going to have to go to the max depth, but at the same time, it's also going to have to check for the branches.
Yeah, so when you say it's also going to have to check for the branches, what is it
Oh.
doing when it checks for the
It's
branches?
going to have to check each of the children and find which are about to go.
That's correct. It's going to have to check every one of the children because it has to perform an insertion. So it's going to compare for each letter, D, for each letter in the word. It needs to compare that letter against all B letters at a given level to determine where it is to be inserted. And so doing that, B comparisons, D times, gets us D times B. Any questions on that? Good job. So now let's think about a search. If I am searching the trie, how many operations do I need to perform? Is there any reason for it to be different than an insert? We know it's not worse than an insert. It won't be more operations than an insert because when we do an insert, we have implicitly done a find. So it can't be more than an insert, but can it be less? How so, Elijah?
Because it might not have to check every single one of the children.
Okay.
And once it finds the one it's like the first one, then it would have to check all the ones just with that.
That's part of the answer. But how many of the children at worst would it even have to examine?
Furthest children away.
I'm actually just thinking about this term. This term represents the work at one node, right? So at one node, to do an insert, right, we had all these cells in the array, and we might have to shove something in and then move everything aside to keep it sorted. Given that it's sorted, if we're doing a search, do we have to look at every single one of these? So Pam, you're shaking your head. Why don't we have to look at all of them? True, I can find exactly where to go. What kind of an algorithm am I going to use to do that? It has a name. We've discussed it. We have a sorted array. We're looking for a value. We're going to ignore a lot of stuff. What kind of search is that? So remember, when an array is sorted, if I'm looking for something, I can look at the middle value. And if my value is less than the middle value, I can rule out half of it. If my value is greater than the middle value, I rule out the other half. And then I repeat the process. I rule out a quarter, and then I rule out an eighth, then I rule out a 16th. How many rulings out do I need to do? Not too many, right? Because if I've got this value b, I'm getting rid of half of it on every comparison until there's only one possibility. How might I solve for this value k? I'll review it with you all.
Oh, log K.
Right? So we do a binary search at the node. which takes log base 2 of B comparisons. And so searching is just D log 2B. Remove then is just doing a search and marking it as false. So remove can actually be D log 2B. Although if we do the cleanup version, then there's some more work, because when we do the deletions, we might have to collapse our arrays and so forth. So the quick remove is just D log 2B. The memory saving remove is D times B. How about a traversal? How many operations are we going to need for a traversal?
Probably D.
How did you come up with D for a traversal?
Well, we have to do the depth. Well, no, it has to be. No, not that. It should be. I know that there should be an in because we have to search for each number of nodes.
So for a traversal where we enumerate every member of the set, imagine every node contains a member of the set. How many operations are we going to need?
Probably just in.
Correct. Traversal is n operations because we need to visit every node. If we fail to visit some node, we may have missed an item that we need to enumerate. So this is a really interesting list. Note that the only operation that depends on the number of nodes is a traversal. So now we're going to get really intense in our analysis and think about what is the relationship among these values. So let's list them out. There's n, the number of nodes, d, the depth, b, the branching factor. Let's see if we can construct some inequalities to describe the probable relationships between these values given a sufficiently large number of words. So you're throwing in n English words, just words right and left are coming in.
N isn't affected by it too, so.
They're not necessarily affected by each other, but given a data set like words in English, we can draw some logical conclusions about their relationships.
No, I was referring to N, how N is probably just, it's on its own.
Not really, no. We need to be able to state relationships among these so that we can understand the implications of these values here. What is n likely to be less than or greater than d?
Probably greater.
Okay, why greater, Graham?
Because it is getting to include all the nodes, which means it's going to be a fairly large number compared to just the max depth of the entire tree.
That's true. There's one little extra insight I'm still looking for. But that's true, and it's important part of the insight. If we just think about adding dozens upon dozens of English words to the trie, even hundreds or thousands of English words. So you've got n in the hundreds or thousands. Why would n be greater than d?
Because it's based on the number of nodes that are active in the tree based on the number of active letters.
We don't even need to think about the tree.
Max depth based on the connections and
Right. And so how does this let us conclude something about if I'm adding English words, why is n greater than d? D being relative to the length is a crucial part of the puzzle. If I have an unabridged dictionary with 1,000 pages, each of which has 100 words or whatever, as I'm paging through it, how long is the longest word I'm going to find? Is it going to be thousands of letters long? Hundreds?
We don't know that. We don't know because.
What do you mean we don't know?
Relative.
Somebody give me an upper bound on the longest possible word you know of in the English language. Okay, how long is it?
It's like 26 letters.
Something like that. So Jake, racking his brain, came up with maybe a 26-letter word we all know to be ridiculous. See, this is all about understanding the data itself coming in and not necessarily the data structure. N is not just bigger than D, it's a lot bigger than D. Because English words tend to be short compared to the number of words that exist. That's just an observation about the data set. And whenever we're thinking about data structures, we often have to think about what's the structure of the data set itself. And how does that illustrate what makes sense in terms of the structure? Now let's think about B, the branching factor. What's the relationship between N and B given English words? Is it going to be less than B, bigger than B?
It is going to be bigger than B because the branch factor. The factor is based on the.
Using the data set. Using the data set, how do we explain that relationship? We use the data set to explain this because English words tend to be short. What about the branching factor? Yeah.
There can only be a maximum of 26 per B, whereas, like we said, there are maximum thousands of words per N.
Exactly. N is going to be a lot bigger than B. In fact, if we look at D and B, we can comfortably bound them, right? For English words, if we make everything all lowercase, both D and B are probably less than or equal to about 26. Now we come back here. Expressing these algebraically is extremely important because it's how we carefully and rigorously document our assumptions. But what I'm assuming down here is that D and B are effectively constants. They don't really grow as the number of inputs grows. Now, in order to reason correctly about the behavior of a trie, you do need to know what those constant bounds look like. But for a data set like English words, these wind up becoming constants. In other words, add, search, and remove become, in effect, constant time operations in terms of N. N doesn't make an appearance in any of these. So they're effectively constant time operations. Now, if you posit a different linguistic system than English, this could rapidly change. For example, when we think about the maximum depth, if we switch from English to, say, Hungarian, Chinese is coming next. Wait a second. If you switch from English to Hungarian, Hungarian words can become arbitrarily long. They can add prefixes and suffixes all day long in Hungarian to expand their words. They can have words with 50, 100 letters. It's still generally boundable by a constant, but it's going to be a bigger constant. Now, B, this is where Chinese comes in, right? If you've got a language like Chinese that has tens of thousands of characters, now your branching factor gets really big. And maybe a trie isn't as good a data structure. But
Should only work for certain dictionary. Try is only good for small.
For small d and small b. Yeah. But if you've got small d and small b, which you frequently do, a trie is as good as it gets. All right, I'll see you all in lab tomorrow.